Good morning, everybody. I just want to make sure you can hear me when I walk away from the podium. Can you still, all of you hear me? Great, thanks a lot. So I just want to first get a bit of an idea of how many of you are, there are two ways I can actually do the presentation today. I've sort of made it a bit flexible because I wasn't sure how many of you are interested in how LLMs actually work. First of all, LLMs are really large AI brains, okay? They're tiny little brains like compared to ours, but really large compared to what was possible 5 years ago. And way larger than anything that was possible 20 years ago, 10 years ago. And the properties of these things are, it's mind-blowing what they can do. For those of us who've been in it for a couple of decades, it's just, otherworldly seeing the capabilities of these systems, some of which I'll try and show you. The way I'm going to do it is I've actually built, not me, my colleague, I'm doing this talk with one of my friends, Arvind. Arvind was a researcher with me. We ran a research lab together for about 15 years. And Arvind was also the CTO of a company called Bicycle AI, which was a Y Combinator company, and he was in California for that. They were Axel funded. They tried to do customer service agents. They tried to build AI systems that could sort of handle a conversation with a customer, and so handle customer service for you. And this we tried about 10 years ago, which was just the wrong time, right? We'll show you what we do if we were doing this company today, right? If we were building this today, if I had to handle pizza ordering for Domino's, what would I do? What would I do? And we actually built this, and we're going to run it and show it to you at the end, right? But that's the end, okay? For the next 30 minutes, I can sort of go one of two ways. I can sort of help you understand what goes on inside an LLM, okay? Just what's happening inside those big brains of theirs, okay? Or I could go the business side and talk more about how you'd possibly use these, what you'd tell customers, what you'd be worried about, more on the business side of it. So how many of you are from business or service delivery functions in a company? Okay, that's a lot of you, all right. How many of you are from technical engineering backgrounds? My goodness, you guys win, actually. So those of you who are going to be a little bit baffled with the tech side, please bear with me. I'll if you have any questions, I'll be happy to answer them. And I'm going to try and make this sort of interactive as well. So anytime you have a question, just raise your hand, but sort of one question in 5 minutes would be nice. Not more than that, okay? So let me just get into it, okay? So what are you going to learn? What's an LLM? I'll give you some ML background. If you want more, at the end of this time, okay, guys? I'll talk about how you can use an LLM in a product, and I'll show you how you build an order-taking robot, right? So supposing you guys are going to work for Swiggy or Domino's, what do you do, right? So let me first tell you what large language models are, okay? These are neural networks. What are neural networks? Very, very simple, right? They're just a bunch of wires like these, all right? So inside of these most amazingly complicated LLMs that you're talking about, there's something very simple taking place. All that's happening is you have an array of numbers. That's the inputs, okay? So let's say the inputs are right at the top. This is where you give it a set of numbers. And then you give it a bunch of connections. There are a bunch of multiplications. Each line represents a multiplication, okay? You multiply what's called a weight, all right? Now, this is very interesting. You just multiply some floating point number, which is called a weight, and you bring it down to the next line, okay? So this, whatever, your inputs multiplied by a bunch of numbers is what comes here. That gets multiplied by a bunch of numbers comes here. That gets multiplied by a bunch of numbers, and you get an output. It's that simple. It's multiplication. Even a child can do it, right? That's really what's going on inside a neuron. But in large language models, you have a very large number of neurons. I've said 1 billion here, but most of them have like 100 billion neurons. And it's getting bigger and bigger all the time, okay? And they're trained in a particular manner, which is very interesting, which I'll talk about in a little while. So if you have these four things, you've got a large language model, okay? And that can do all kinds of magical things with language, and you'll actually see it working, okay? So how does a neural network work? You've got these input nodes, and you've got these output nodes, and you have a bunch of hidden nodes, right? This was a huge thing in the year 2012, about 15 years ago, right? This was so big because machine learning people at that point had not figured out how to do more than one row of neurons, if you will, right? Getting past one row of calculations and learning to do that was so difficult. We used to do things called statistical models. So in the year 2006 to 2012, the whole world went through an explosion of statistical modeling for machine learning, right? And this was a huge advance over what used to be rule-based systems. So the first time I tried to build customer service bots was around the year 2000, okay? So I was working for a professor, and he went to Dell, all right? So he went to Dell, and that was the dot-com boom time, towards the end of the dot-com boom. He got money, he got investors, and he said, I'm going to build customer service agents using AI, okay? And they used to build these using rules at the time. You'd write a lot of rules and do all these fancy inference schemes around it. And he said, I'm going to answer questions about Dell products doing this. And 2 years later, his company was bankrupt, and I talked to him, and I asked him, hey, what happened? And he said, every time we added an additional rule, everything would break. Things would go really bad. So to solve that, people came up with what was called machine learning, which is you give it training data, and then it learns from the training data. You don't have to write rules. Okay, but for a whole decade, 2000 to about 2010, 2012, those models used to be very simple. About one layer of calculations was all they could do with statistical machine learning. It was really hard to do more than that. And so what deep learning allowed you to do, it's called deep because you can have multiple layers. Okay? So many multiplications can happen before you come to the output. It's that simple. Okay? It's that simple. All right? And this became possible to do because you had very, very powerful computers, right? GPUs which could do these computations for you. So what you do in a neural network is you take a bunch of numbers, you multiply some weights, and then you squish the numbers a little, okay? You squish the numbers a little. This is called a nonlinearity. You introduce a nonlinearity, and you do this again and again until you come to the output. Okay, so there's a neuron, you multiply some numbers, okay? You take the inputs, you multiply numbers, then you squish the outputs a little. It's that simple. Okay, so you get a squished result. So in this case, I've only squished the bottom. The bottom was, when I multiplied the numbers here, one of the numbers was negative. I squished it to make it all positive numbers, okay? So you do something to make it nonlinear. You just don't want multiplications. You modify it a little. You do this again and again and again, and the last number that you get is the prediction. So the model says, if I have this, 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 and this, if my prices are da-da-da-da-da, then this is probably going to be my cost of producing the product next year, okay? So your prediction is a number there. At the end of it, it can be many numbers, or it can be just one number. So you have a prediction, and the way you train a neural network is you compare it with real data. You take previous year's data and you say, oh, my costs were these, and these 2 years ago. And this was my final production cost, right? So you take that, you look at the prediction, and then you say, oh, it doesn't match what actually happened. And then what you do is you readjust the weights, okay? So you say, oh, let me adjust these weights, that is, all the weights on these lines, I'm going to change them a bit until the prediction matches the expected value. That's all that a neural network does, right? So you run some numbers through it. If the outputs don't match, you change your weights until they match, okay? And that process is called training. How do you do it? You actually use differentiation. So many of you must have learned differentiation in school. Who's learned differentiation in school? Very good. Okay, you guys are better than I thought. So, rate of change of something, that's what differentiation does, right? So if I want to know what is the rate of change of the output, when I change a weight, I just do d output by d weight, isn't it? So I just compute that, and that tells me in which direction I have to move the weight in order to get my desired output. That's all that training a neural network involves, okay? It's that simple. So you do this, and you can do this on a lot of different kinds of data. You can do this with images, right? Because images can be turned into numbers. You see that? I've basically taken that and represented it as, a grid of numbers. Do you see that? So here again. All right, wherever there is a line, I've put a number that's non-zero, and I can represent an image as a grid of numbers, correct? Similarly, I can also represent language as numbers. How do I do it? If I have a sentence, my name is Arvind, I can take each word and represent it with a vector of numbers. You get it? So I just say, I'm going to put this word, I'm going to give it this sort of address, right? So I give it a vector of numbers. You can see the vector of numbers down here. Sorry. Yeah, that vector of numbers, I assign one vector per word, okay? Each word gets a vector of numbers. Suddenly, I can give this to a neural network. You see that? If I can represent any information with numbers, I can feed it to a neural network. And then I can get predictions on it. So it doesn't have to be prices. It can be weights. It can be shipping times. I can do predictions on a lot of things, okay? I can also do predictions on language, right? Because I have a sentence, I take a sequence of numbers, and I pass it to the neural network, I can get an output prediction. You can also do this on parts of a word. What really happens in an LLM is they don't go word by word, they go few letters at a time, okay? So my name is Arvind probably ends up being broken up like this, okay? Again, your sentence gets turned into a sequence of numbers. When you have numbers, a neural network can deal with it. So what are large language models? Again, like I said, they understand language or sequential data. Why do I say sequential data? It does not have to be words. It can be sounds. I can, give it speech. I can give it, videos. I can give it anything that I can represent as numbers, and it can deal with it, right? And I've said that this has to be kind of large, and we'll see why it has to be large, okay? So this is what a language model is, okay? You heard the term LLM, it stands for large language model, right? Why is it called a language model? A language model is any machine learning system which tells you the quality of a sentence, all right? So if I give it a sentence, the cat caught the mouse, it gives it a high score if this is a correct sentence. This is a correct sentence. The cat caught the mouse is a good sentence. And so it says in the English language, this is a good sentence. It gives it a high score, okay? So it is a function. A language model is a function which assigns a high score to good sentences, a higher probability in technical terms, all right? So if there is bad grammar, cat, mouse, the, caught, that is not a grammatical sentence. It has to give it a low score, okay? Even if the sentence is grammatically correct, but it doesn't mean anything. The banana ate the computer. It has to give it a low score. So it's not just grammar. It's not just a parser, okay? A language model has to say, this is not making sense, and it has to give that a low score, okay? So that's what a language model is. Am I clear about what a language model is? Okay, it's not just a grammar parser, it's a little more. It's something that says, that sentence in this language does make sense, okay? So it's this kind of thing that tells you that, when you give it a sentence, that sentence is a good sentence in the language. This is the way we used to build language models 20 years ago, okay? This is a statistical language model. The way we do it is by looking at the probability. If I've already said the cat caught the, what is the next word going to be? Mouse, okay? So all of you can say that, right? And that's what it looks for, right? It looks for a high probability for mouse, given that I've said all this. The cat caught. What is the next word going to be? The cat caught the or right? So it assigns a high probability to the next word given what you've said so far. So that's what's called a language model, right? This is how you would build it in the days of statistics, okay? Except this was too hard for a statistical system to do. Why? Because you have so many words to remember, and most statistical systems, they weren't deep enough. They couldn't remember that many words. So what you would do in the world of statistics is you would only look at the previous word. You would say, oh, I've said the. What is the next word? Very hard to tell, right? And you'd expect it to say cat, but it doesn't know more than the previous word that I've said because it just can't remember enough. It's not a big enough model. Okay, so this is why most statistical systems didn't work out too well. And then along came neural networks. They figured I could feed data to neural networks sequentially by sharing some weights, okay? So you would, that is the neural network that you saw, but after reading one word, my, okay, I'm going to ask it to predict the next word. You see, those are numbers, and these are numbers, okay? So I see the word my, it predicts the next word, name, all right? And then I feed in the name again to the same neural network. So I say, hey, now I'm going to say name. Remember that I said my inside your neural network states, okay? In the hidden layers, please remember that I said my before. And then tell me what the next word is. And it says is. Then I feed in is, and I say, please remember that I said my name. I'm telling you now the next word is, what should the next word be, okay? This is how you build a neural network language model. It is just the neurons that you saw, right? This whole array of neurons in multiple layers, but I keep feeding it the word it gives me, okay? So I give it the first word, it gives me a possible next word, I feed that in, and I say, give me the next word. Feed that in, give me the next word. You get it? This is how a language model actually works, okay? And what they found when they did this was it was amazing, all right? So I can start feeding in things. Here, there's a guy called Andrei Karpathy in 2015. He ran this experiment. He fed in words letter by letter, okay, into the neural network. He would feed one letter, it would output the next letter, another letter, the next letter, and he found that this could generate, Shakespeare. Okay, it could generate phrases that were Shakespearean-like. It could generate code. A lot of the things that you do with neural networks now, right? So you have, you have all these things you can do, autocoders and so on, where you get coding suggestions when you start typing. They started doing that in the year 2015 with very, very simple neural models. These were much, much smaller than what you have today, okay? There were a few thousand neurons in there, maybe a few tens of thousands, okay? What you're doing now is 100 billion neurons, okay? And these could remember so much. This blew us away. In 2015, I read this article. This was a blog at that time. And I said, this is impossible. Because I'd been working with statistical models all those years. And I said, it just can't be done. How is this even possible, right? It was like mind blown, phase one, okay? And then they ran equations through it. They gave it a few equations and saw whether it could. And this is a whole article on maths that tiny neural network started generating. The math is all wrong. But what was amazing is that it could even generate this. Okay? A tiny bunch of neurons sitting in there. All right? So what he says here is very interesting. He said it hallucinated the algebra. And today when you work with ChatGPT and some of these large models, you get hallucinations. If you ask it a question and you're not careful, it'll give you completely imagined answers. Because it's a language model. Its main priority is making sure it generates language correctly, not giving you correct information. That's not the objective it was initially trained for, okay? So it makes sure it gives you a very nice answer. It has not been trained to give you facts correctly, okay? So we'll tell you what happens later to get correct facts. So this is how we started making neural networks bigger, okay? In 2017, there was an amazing paper that came out of Google. It's this paper about a kind of machine learning architecture called a transformer. Okay? I won't go into the details unless we have time at the end, but basically, you can give it a whole bunch of words, okay? And it does what's called attention over the words. Okay? Attention mechanisms are a technical thing which you can read about, or if you have time at the end, I'll explain it to you. But it basically, when it reads a word, it looks at the rest of the sentence and associates the words with each other. And then it goes up to the next layer, okay? And it does this over a lot of layers, okay? So that, what you saw here, was one block, okay? Encoder block. It repeats that block many, many, many times, and it looks at one sentence at one shot. So you say, okay, I assume a sentence is going to have a maximum of 1,000 words. You give it some arbitrary window, and then you start looking at all the words in the sentence at one shot, okay, at one time. So that's why it has to be so big. And then every time it's looking at a word, it associates it with every other word. So it's building associations between words. It's learning the meanings of sentences as it goes up. And it does this over a lot of stacks, okay? It does it like many, 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 many times, and finally it creates a representation. And then it generates the next sentence, if you will, okay? So that's what transformers do, okay? These are very large-sized language models, okay? And these started producing amazing, amazing results. And you can see how the size of it went. They started at about 65 million neurons, okay? When I say parameters, I mean neurons, the lines that you saw on my diagram. They started with about 65 million of those, and context window is the number of tokens, right? If it breaks it up into parts of words, and it can take about 512 word parts. That would be about 100 words, okay? It can digest at a time. And now they've reached about 200,000 word parts. I would say maybe around 40,000 words. You can feed it in one query, if you like, right? And the size of these neural networks, it's crossed 1 trillion. So GPT-4 they're being very secretive about how big these are, but I've seen estimates vary from 200 billion to 1 trillion neurons in that one. So very large language models can acquire a very sophisticated understanding of language from just raw text, okay? This is very important, being able to learn from raw text, because there's lots of raw text, right? I feed it the internet. I tell it, here's the internet, learn about language from the internet. And it can do that, okay? So you can train them using what's called self-supervised learning, which you already saw. How do you do self-supervised learning? You give the neuron, some text, and then you say, predict the next word. There are many other ways you can do it. You can take away a word from the middle of the sentence and say, predict what that word was, okay? Or you can take two sentences, give it two sentences, and say, were these sentences one after the other? I can sometimes invert them, and it should be able to tell, no, these are not one sentences. These are not two sentences that should follow one another, right? So you can train it on raw text by giving it a lot of these tricky problems to solve. And as these neural networks solve these problems, because you've given them clues, you've said, hey, this is not how two sentences should be. This is how they should be. These are the clues you're giving your neural network. Slowly, by looking at trillions and trillions of sentences, the neural networks start to understand human language. Okay, that's how they are trained. This is called pre-training, okay, or self-supervised training. So with very large language models, in 2020, when GPT-3 was built, okay, GPT-3 was a lot of billions of neurons. When they built it, they suddenly realized, good Lord, this thing can learn things we never thought it would learn, okay? So basically, they were asking it to continue certain things, and so they would say, okay, generate the next few words and give me the next sentence. And then they tried asking it, tell me, what is the sentiment here? Was he happy? Was he sad? And they found it could answer that, okay? So they found that once you reached a certain size, once you went above 100 billion neurons, with about 10 examples, it could learn any task, pretty much any task, to about 60% of the performance of a state-of-the-art model. So if I give it a question answering task or I give it a chatbot task, okay, can you chat with me about something, psychology? The best models in the world that are trained to do that, it could reach 60% of their performance with only about 10 examples, and it's in this paper. I put a lot of these papers here. I don't know if you're going to get the slides later, but you can then go to the papers and read these if you like, okay? So one of the first diagrams they do is they show you smaller models. It takes hundreds and hundreds of examples, thousands of examples. As it crosses 100 billion, suddenly, 10 examples, you get 60% of the performance, which is mind-blowing. You just tell it 10 times how to do something. You give it 10 demonstrations, and the thing learns to do it. Okay? They found that these large language models, LLMs, could do that, okay? Which is, they were blown away when they found this out, right? All of us sat there and we're like, corporate guys lying? Or is this something real? Can it really do this? Wow, you know? So we were blown away a second time when this happened in 2020. Okay? And then they started working on, how can I make it do other things that I'm interested in? Like, you know, can I make it answer questions? Can I make it have a conversation with you? Right? And so then they came up with a solution. They said, once I've pre-trained it on trillions and trillions of sentences, the pre-training method that I told you about, I will then fine-tune it. I'm going to fine-tune it to have a conversation, to answer questions, okay? They call this the fine-tuning step. And there are two methods that are generally used. One's called supervised fine-tuning, and then there's something called reinforcement learning. Reinforcement learning is what is used to train robots, okay? So that was used to train these. Basically, what they did is they made it generate two answers for everything, okay? And then a human would just pick the right answer, right? They'd say, oh, this answer is better than that. And that, you remember I showed you in the beginning, when you train it, you show it an expected answer, and this is what you've predicted, and then you feed that information back, and the neurons adjust themselves. So they did that with these reinforcement learning things. They just made it give two answers out. And then you can do that using, for the techies, there's something called temperature that you adjust, right? Those of you who've used large language models or any kind of language model, you set these temperature values high enough that it's being creative. And then you take two of the answers that it gives you, and then you say, hey, this is better, and you can compute a loss from it. Once you compute a loss, it can automatically learn from the loss, no matter what size it is, blah, blah, blah. And what they found is once you went above a certain size, it can learn things without forgetting earlier things that it had learned. So it wouldn't forget what it had learned from the trillions and trillions of sentences you gave it, but it would learn this new skill to chat with you or to answer questions from you, okay? And that's how they built ChatGPT, okay? Oh, okay, I think I'm almost out of time, unfortunately, but they trained ChatGPT on just something like 13,000 examples of all the different things that it can do. Can you imagine that? It can do like thousands of different things. That's like around 13 examples of everything. And that's all they trained it on, and it learned to do all these amazing things that you've seen it do. Okay, so here are some of the things it can do. Classification, extraction. I'll come back to this if we have time later, but classification is basically assigning some kind of label. Okay, that's one of the tasks you do with a machine learning model. Then there is something, so these were the kinds of things they used to train it, right? They told ChatGPT, oh, look, blah, 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 can, rate something on how sarcastic this is. How sarcastic is this? They gave an example of it, and then they basically gave these as examples for it to do, okay? And they adjusted it with just 13,000 examples of classification and extraction. Extraction is locating some information. If I ask you, what's your name? What's your name, sir? What is your name? Atul. That was extraction, okay? I asked him to find some information for me. He gave me the information. Extraction, okay? Classification is your name Atul? Yes. That's classification. He had two choices, yes or no. He picked one, classification. So most humans operate as classifiers and extractors in a conversation that one person is dominating, okay? So this, you can do lots of kinds of extraction, relation extraction, named entity extraction, and they trained it on that too. They trained it on a lot of things like that. And once they trained it, they found they could do this, right? So you ask it the purpose of the variable C in the code, okay, without the fine-tuning, it would have just gone on giving some gibberish. But with the fine-tuning, it can now talk about C code. Can you believe it? They've given it just a few instructions, maybe about C. Okay, they've talked about Java, they've given it all of this. It just suddenly starts understanding C code. Okay, it's unbelievable. Okay? So this was the really shocking paper, came out 2 years ago, guys, just 2 years ago. Okay? And lots of other things that it can do. You guys can go over the slides later if you get it. And you can see one of the interesting things about this is it can be very costly to train a large language model. When transformers came about, it would cost about $1,000 to train one transformer. Okay? But remember, you have to train it multiple times to get a good model. So 1,000 each time you train a transformer, okay? Right now, it's at like about $78,000. I read it's about $200,000 for the Gemini models that Google is training. It's beyond my ability to do this, okay? Which is kind of when I stopped consulting. I'm like, I can't build this for you guys. I can't do this. But how do you build an order-taking bot? I'm going to show this to you very quickly. We prepare for 3 types of interactions. Now, this is based on a paper. I'll just tell you the name of the paper. Go ahead and read it, guys. It's really worth it. It's called AutoGen, okay? AutoGen, multi-agent conversations. Just Google this paper. You'll find it. It's a paper from Microsoft Research along with a few educational institutions. They talk about, how do you get a large language model? Since you can't train your own, use somebody's large language model. Now, you can't change its behavior by fine-tuning or anything because it belongs to that company. So what you do is you program the model conversationally. You give it instructions such that it'll do whatever you want it to, okay? So that is what you can do. And it's amazing what you can do with just telling the model cleverly what to do, right? And you can, what this paper did, the AutoGen paper did, is it said you can create multiple agents. Agents are nothing but role-playing behavior of the same model. You can tell the model to play the role of a helper. So a user who comes to the website will want information, they will want to place an order, and then they will want to know what happened to my order, okay? So those are the 3 things they will ask for, right? There'll be information seeking behavior. What's on the pizza? What can I order, right? Tell me more about the toppings that you have. Then they will place an order, okay? And then finally, there will be information seeking. Where's my order, okay? So what you do is the helper agent, you instruct it like this. You first give it a role to play, okay? So instructions, good instructions, these are called prompts. Good prompting technique, you give it a role, you specify the role. You are a friendly, but you're a very rule-bound pizza ordering assistant, okay? So you tell it that. And then you tell it about the pizza, right? Since this is the helper agent, people are going to come to it for information about the pizzas, you tell it about the pizzas. There are 3 sizes, small, medium, large. You can add any number of toppings, and the toppings can be one-off, and you give it a list of toppings. And then you say, large pizza should be enough for how many people, okay? And allergies and other information. And then what you do, so this is information that is grounded on. So you tell it, right? You have to answer the query based on this information. So you ground your prompt. You force it to go back to this. That reduces hallucinations. Okay? So that's what you do with the helper agent. Then you have an order-taking agent. For the order-taking agent, I've written it in 2 parts. Firstly, you tell it about the pizza so it knows what to take an order about. And then what you do is you say respond with JSON. JSON is a format that you can use to pass information to a Python function, okay? So if I'm writing code in some programming language, this is a format I can easily use to call that code, okay? So the cool thing about these models is LLMs have now been trained to respond in a language that your computer can understand, okay? So the order-taking agent is going to have to go into Swiggy's or Zomato's computer systems and place the order. So it's going to respond in JSON, and it can, nowadays, agents can automatically call Python too and return the result to you, okay? So the final thing is to call a function to check order status, right? So Arvind wrote this function, and he left these comments here. And the new frameworks that we have, there's a framework called LangChain. Check out LangChain and LangGraph, okay? Autogen, LangChain, LangGraph. You'll have pretty much everything you've learned here ready for you guys to use, okay? So in LangChain, there are frameworks which can take a function like this and construct everything that the LLM needs automatically. So he just gave it this. He said, hey, if somebody asks about order status, just go to this function. And what the LLM did is it looked at the function, looked at the comments, and it figured out everything. Okay? So I think with that, we should be able to, okay, over all of this, there was a supervisor agent which picked which of these agents the conversation should call next. So I'm going to, this is the kind of graph, right, that was constructed. You have a supervisor that picked which agent to call. So this is the autogen part, okay? Choosing multiple agents. The reason we split it across multiple agents is that way the LLM doesn't get confused. And now we'll do a demo of it. Can you go ahead? You have to forgive me. It's a little difficult to read. I'll sort of, listen to it. And if you, don't get some of what's going on, I'll stop it and tell you what he's saying. So Arvind built a notebook, and then he started running one of these, this order-taking thing. And he shows you what happens. There's classification that happens. There's extraction that happens. So try and spot it when it happens there, okay?
All right. Let's take a quick look at our pizza order bot. This bot is built using LLMs and LangChain and uses a multi-agent architecture. Our current bot consists of 4 different agents. A supervisor. This agent is responsible for deciding which sub-agent would actually be most suitable to respond to the given user query. We have our helper bot. The helper bot is responsible for answering user questions based on a policy document. The policy document can be a general English document. You can update it with simple English sentences. You can add additional information to it.
So this is what you saw, right? The helper agent's prompt is what he's talking about now. I realize this is too small. You can't read it in the back. But, the helper agent prompt, this is what the pizza is, provide information about the pizza from this information. That's what's in there. It basically says, these are the pizza toppings, large pizza, small pizza, medium pizza, right? That information's what's over there.
And the helper bot would answer user questions in compliance with the policy doc. We have our order taker bot. This is our meat of our agent, right? It's a pizza order taking bot, right? So this agent is actually responsible for ensuring that the order is, meets all the requirements. We have all the sufficient details to deliver the order. We also have an order status agent, which can give you the status of your order after it has been placed. Okay, so let's jump right into the demo. Okay, so let me just, my wife is allergic to peanuts. So let's right away ask about peanuts first. Okay, so
So you can see, he basically typed up there, my wife is allergic to peanuts. Do your pizzas contain peanut? Okay. The response that it got is, our pizzas do not contain peanut oil. However, please note that all our products include milk-based ingredients. Because up here, we've said they all contain milk. So it's kind of saying that.
Seeing the log statements for the bot as well as the final reply. So as we can see from the logs, stated that the helper agent was the most suitable to respond to this query. And the helper agent replied with, our pizzas do not contain peanut oil. However, please note that our all products include milk-based ingredients. Yeah, and as you can see from our policy doc, the allergen information mentions that, the chocolava cake contains peanut oil, but not the pizzas. Okay, so now let's complete our order. I want to order a pizza sufficient for 2 people. So I don't have...
So you see, he says, I want to order a pizza sufficient for 2 people. This is a very difficult problem to solve if you're building agents. He doesn't say, I want a medium pizza. Okay? So it has to infer that he wants a medium pizza because that's what we've said somewhere is sufficient for 2 people. Okay? Let's see if it's able to do that.
To be direct, even though our policy doc says that, pizza has to be small, medium, or large.
You can see the reply is, you've chosen a medium pizza. So it figured out that he wanted a medium pizza. And then it asks, it doesn't stop there, because then it leaves the conversation hanging. We've asked it to be, to play the role of an order taker. So it says, what topping would you like to add? Okay? It says, we have, and it lists all the toppings. We have capsicum, tomatoes, olives, mushrooms, onions, jalapenos, pineapple, and pepperoni, which is exactly what we've given here in the description.
I can depend on the bot to make reasonable guesses based on the policy doc or otherwise also from the world information. So the bot has inferred that medium pizza is sufficient for 2 people. And again, this is in compliance with the policy doc. And it has asking me for the toppings. How about pineapple, tomato, and mushroom? All right.
So yes, so he says, how about pineapple, tomato, and mushroom? This is information extraction, right? He has said, how about pineapple, tomato, and mushroom? Try and get somebody to understand that he means he wants. He's asking, how about? He doesn't say, I want. Okay? Most traditional systems look for keywords like I want, and they say, oh, he's trying to place an order for these toppings. He says, how about? And it figures out that he wants those toppings. Okay? And it says, oh, I got it, a medium pizza with pineapple, tomatoes, and mushrooms. Okay? Would you like to add? And it tries to sell him more things. So it says, would you like to add any side items such as garlic bread, chocolava cake, and chicken taco? This was in the function that we gave it. We said in the function, these are the sides we can accept in the function. Okay? And it just figured out from that, I can let you order these sides. It wasn't even in the policy document that he has given here. It figured it out from the code, okay, and the description of the code that was in it. Oh, go ahead.
Have a medium pizza with pineapple, tomato, and mushroom, and it's asking me for the sides. But never mind. How about if we go for a non-veg pizza today?
So he says, I want to change it. I don't want vegetarian toppings. I'm going to go for a non-veg pizza. Go ahead. So he says, make it pepperoni. He's typed, make it pepperoni up there.
So as you can see, the bot is smart enough to understand that I want my pepperoni topping to replace the pineapple, tomato, and pizza. And I could have added pepperoni topping also if I had made a statement like, also add pepperoni. Okay, let's just confirm the order with no sides.
So then it asks, do you want sides? It's changed everything. It's changed the toppings, thrown away the old toppings, added pepperoni, and then it asks for sides. He says no sides. And it says,
okay, so our order is placed now, and we have even been allocated our order ID.
It's given him back an order ID.
Let's have a look at the actual.
And now he basically asks about what's happened to my order. Okay? He can change what's in the DB, all right? He can change the database thing. So he modifies it. He says it's dispatched, okay? Because that happens inside Swiggy systems. He changes the status to dispatched, and then he asks about it. Go ahead.
DB should have our order placed right now. I forgot to quit the chat. Okay, so our order DB is there, and our order is in pending state. Let's try asking the bot for our order status. Where is my food? Okay, so the bot is intelligent enough to understand that it needs an order ID to respond to the status of the food. All right, and we know the order ID is pending. So let's suppose now an external API hits the bot and marks this order as complete or dispatched. And let's ask the bot for the status again. This time I'll provide the order ID right away. Cool, my order has been dispatched and is on its way. That's all for this demo, guys. Thank you.
That's it, guys. I don't think, do we have time for questions or a little bit? Okay, a few questions probably because I think they have another speaker waiting. Yeah, go ahead.
From University of Illinois, Urbana-Champaign. So, so how do you think this kind of a system can be applied in any a mental health or where the emotions are involved? Like someone recently we got to know that because of high demand for mental health professionals, people are using ChatGPT kind of for their immediate emotional support. So how do you think, or what kind of things we should be mindful of when we are having this
I
kind of
actually haven't done that use case. There are 2 startups in Bangalore which are working on this. I'm forgetting the name of one, but one of my friends, Amrut Biar, you can look him up on LinkedIn. He's working on this. He's been working on it for the last 10 years. So contact Amrut Biar, one of my friends on LinkedIn, and see if you can reach out to him. He'll be better positioned to answer that question.
Thank you.
Yes, please.
Is there a forward process by which we can kind of align to our needs, or is it even now trial and error kind of data, garbage in kind of stuff? So, say as a company wants to align a LLM for a particular purpose, what is the best way to go about it?
Sure. So the question is there a formal process by which you can get it to work for you, or is it trial and error, right? Can you align it? So alignment is that second step of training a model that is too expensive. Those models are too big, take too much processing time. They won't align it again for you. Except, I guess if you're Facebook, Facebook has put out these models called LLAMA, Llama models, which you can download and then you can mess with it however you want, okay? So that you can probably align yourself, but at your expense, it'll cost a lot of money, okay? But what you can do is you can instruct it, you can give these prompts in certain ways to get the results you want. And there's a lot of research going on for the last 2 years on this. So you can go and look up researchers at OpenAI, some of them have blogs, and they talk about the latest prompting techniques. So there are techniques like React, R-E-A-C-T, you can look up the paper, React prompting. There's something called chain of thought prompting. So you basically try and get it to reason, and then you use the steps of the reasoning to improve the performance. Or you use retrieval, augmented generation, right? To prevent hallucination, to ground it to certain truths. So there's a lot of frameworking you can do around it, and there are standard methods. Look up RAG, retrieval augmented generation. Look up React, look up prompt, look up AutoGen, which I told you. That's the latest paper from about 8 months ago. Yes, please.
Great masterclass, by the way. It was phenomenal.
Thank you.
I guess my question is more around AI versus Gen AI, right? Which is Gen AI using large
Gen AI
language.
versus?
AI, conventional AI.
Okay.
I'm in the engineering domain, so when I see a lot of these large language models, use cases, etc., it's all about trying to converse with the end user and making that more sophisticated. Is there a use case for these things or more sophisticated use case from Gen AI in the world of engineering, where you can probably get ready-made models that can be used for these use cases, like product development or whatever?
That's very good. It's a very good question. So the question was, can you use it in engineering use cases, or is it more for conversations or conversation-based stuff? So you must bear in mind that since the training cost is so high, they can do it once in a few years, okay? So what that means is, and they also need so much data which comes from what's on the web. Often engineering or very technical documents are not on the web. For example, medical record analysis, you can't do it because it's not outside, it's not public usually. These are very private documents, and they're never going to feed that into that. So for certain use cases, you may not be able to use Gen AI, right? It's more for things where they can get a lot of data online. I chose pizza because there'll be a lot of pizza-related conversations. There are even data sets online. So it's probably going to do very well on that. So you have to be very mindful of your use case. If there's not a lot of public data on that use case, it's probably not going to work for you. I suppose, do we have time? I'll wrap it up, but if you have any more questions, you can meet me outside. I'll be just standing outside.
So one last,
sure,
is this presentation available for us?
Is the presentation available to them? I'm okay with sharing it. So you can just contact.
Sorry?
I'm sorry? Yeah. The events at nasscom.in, if you email them, you should be able to get it. Or you can just email me. I'm COHAN@mechanicalchef.com. Okay? COHAN Charlie Oscar Hotel Alpha November at mechanicalchef.com, and I'll send it to you. Thanks, guys.
For more content on tech and leadership, subscribe to NASSCOM YouTube channel and press the bell icon to never miss an update.